Hi, I'm Ugo, and I'm delighted to present you a joint work with Boaz Barak from Harvard and Raphaëlle Crubillé from India Software Madrid. This is about generalizing cryptography to higher-order computation. As such, our work could certainly be of interest to both Track A and Track B people. The starting point of our work was the following observation. Cryptographic primitives like hashing are very often applied to programs. But whenever that happens, programs are seen as sequences of symbols, and their semantics is simply ignored. HS, for example, could take an input a binary string P standing for a program and returns a binary string R standing for the actual hash. As an example, if two syntactically distinct programs are hashed, we expect the two hashes to be very different, even if the two programs are equivalent as for their input-output behavior. So if P1 and P2 are syntactically different but equivalent, we expect the two hashes R1 and R2 to be different. The same observation applies to other primitives, like encryption or authentication. The authentication tag for a program, as an example, does not remain valid if the program changed, even if only slightly, but preserving its behavior. One may thus wonder whether all this is inevitable, namely whether one could build equivalence-preserving cryptographic primitives which act on programs the same way higher-order functionals act on input function. An higher-order functional, as you probably know, act on the input function by seeing it as a black box without having any access to its code. This talk tries to give an answer to the aforementioned question and is divided into two parts. In the first one, we introduce a computational model based on game semantics, which is higher order in nature and in which talking about the typical features of cryptographic primitives is possible. This is remarkable, since even if second-order adversaries are everywhere in cryptography, third-order adversaries have not been considered, at least so far, by the crypto community. In the second part, we will put the definitional framework at work and give some positive and negative results on the feasibility of higher-order cryptography. More specifically, results about influential variables in decision trees by O'Donnell et al. Allows us to show that the most natural form of second-order function could never be pseudorandom. On the other hand, a less natural type of pseudorandom second-order function can easily be shown to exist under standard cryptographic assumptions. Okay, before delving into the details of our game-theoretic framework, let us take a look at how pseudo-randomness would look like in presence of higher-order functions. Pseudo-randomness is a standard and crucial concept in cryptography, which relies definitionally on randomization and complexity bounds. Roughly, a family of objects is said to be pseudo-random if it is indistinguishable from a genuinely random family of the same type. This, of course, only to the eyes of efficient adversaries, since unbounded adversaries can always distinguish pseudo-random constructions from random ones, the first one being deterministic, the second one being clearly stochastic. Actually, pseudo-randomness, as is well known, can be spelled out at order 0 and at order 1, giving rise to generators and functions, to pseudo-random generators and pseudo-random functions. Their definitions, in turn, require notions of order 1 and order 2 efficient adversaries, respectively. But how about second-order pseudo-randomness? This seems elusive, even definitionally, given that notions of order 3 efficiency are available, but are not really what we are looking for here. On the other hand, defining what an order 3 adversary can look like is essential to even give a definition of third-order pseudorandom, of second-order pseudorandom function. Intuitively, however, second-order pseudorandomness seems very hard to attain anyway, given that the input function could be accessed only polynomially many times by efficient adversaries, but that its value can possibly depend on all of them, namely exponentially many. This is, by the way, what a genuinely random second-order function would do indeed. Those of you who know about higher-order computation may wonder whether what we are looking for here is a form of higher-order complexity. The answer is in a sense positive. It is well known that without any complexity constraint on the adversary, modern cryptography would be vacuous. So yes, we are indeed looking for a notion of higher-order complexity. But beware, we won't follow the path traced by Cook and others, in which the parameter driving the complexity is still the size of the input, namely the size of the input function, somehow like in the first-order case. In cryptography, what drives the complexity is taken to be the so-called security parameter, which is not a function, but just a natural number. Take, as an example, pseudo-randomness as we introduced it in the previous slide. There is a natural number n on which everything depends, not only the complexity of the adversary, but also the length of the involved strings. All of the involved strings were strings of length n or of length polynomial in n. The security parameter plays a crucial role in our model, and this is why we deviate in a fundamental way from usual higher-order complexity as introduced by Cook and others. Let us now take a look at how usual game semantics models a second-order function of the kind one encounters in cryptography, namely a functional taking a function on binary strings in input and returning a string. The interaction between the program and the environment, also known as the opponent, starts with an opponent move, which asks the value of the function's result and which is just played there, namely at the appropriate position in the game. To this move, the program replies by asking the value of the argument function. Without it, non-trivial functions could never be computed for very trivial reasons. The opponent, in turn, needs to know the argument's argument, and the program replies by passing the string S1 to it. The opponent finally produces the result, namely another string T1, this way ending the first query. This querying protocol can be repeated many times. This way the program can query the function on different inputs, possibly many different inputs. There is in principle no bound on the amount of times the protocol is repeated. Finally, the program produces the result V, which is a string, based on part or the whole of the interaction history. In doing so, the program can use as many computational resources as needed. But look, is this all what we need in a cryptographic scenario? Well, not really. There are at least 3 ingredients which are missing here, namely time complexity bounds, randomization, and bounds on the length of interaction sequences. These 3 aspects, and in particular the first 2, are key ingredients in modern cryptography, but have not been considered, at least together, in game semantics. There are game semantics frameworks which are probabilistic in nature. There are game semantic frameworks which capture the complexity of the interpreted program. There are game semantics framework on which the length of the interaction is necessarily finite. But these 3 ingredients have not been captured by one single game semantic framework so far. We now briefly describe how a game model specifically tailored for our needs can be built. Games, as usual, are built out of sets of moves for the program and the opponent. They come equipped with a set of legal plays, namely a set of sequences of alternating moves. The main novelty of our model is that this is parameterized on a natural number, namely the security parameter. A strategy is thus a function which dictates how the program should react to the opponent based on the whole history, this is standard, but also on the security parameter. This way, one can, for example, build the game of bounded length strings in a very natural way. The bound here takes the form of a polynomial, not of a constant. This, by the way, nicely reflects the behavior of most existing cryptographic primitives. Again, think about pseudo-random objects as we introduced them a few slides ago. All involved strings were bounded exactly in this way. Bounds on the complexity and on the length of the interaction can themselves be easily enforced, since a strategy is nothing more than a first-order function, and everything is by construction parameterized on the security parameter. One can also give familiar constructions on games, like linear arrow, tensor, and bounded exponentiation. They look very similar to those given by, for example, Island and Wolverson in usual game semantics. Bounds on the length of interaction sequences prevent us from getting usual exponentiation, which is infinitary in nature and which is usually available in game semantics, but not here. In other words, we cannot claim to have a model of multiplicative and exponential linear logic. What is nice about the arrow game construction is that strategies for it can be taken as morphism, and that morphism composition is well behaved, being associative and admitting an identity. The resulting category can be proved to be symmetric monoidal closed, but actually more than that, namely a bounded exponential situation. This being said, randomization is still missing from the scene. And how should we proceed then? Actually, there are at least two ways to insert probabilistic choice into our games. The first one consisting in taking strategies as monadic functions, namely as functions returning distribution of moves rather than moves, and leaving all the rest of the framework unchanged. This, however, does not work, since polytime strategies do not compose if defined this way. Simply, the results of the probabilistic choices are lost along the composition and cannot be recovered, at least efficiently. Another possibility consists in allowing randomized strategies to read random data from a dedicated oracle, modeled through the arrow construction. This way, random bits are always available in the history of the interaction, contrarily to what happens in the monadic case. This is precisely, by the way, what ultimately allows randomized strategies, actually polytime randomized strategies, to compose. And this is the route we have followed. Consider, as another example, a randomized strategy in a simple game constructed from bounded length strings, booleans, by way of linear arrow and bounded exponentials. Suppose, in particular, that the strategy needs one random bit and that its functional argument is queried just twice. To the initial question posed by the opponent, the program replies by querying the random oracle, which returns a bit b. In turn, this influences the way the argument function is queried. The first time, it is queried on an argument made of n many copies of b, and the obtained result is c. Second time, it is queried on an argument made of n many copies of not b, and the obtained result is d. The result of the two queries, namely the bits c and d, are thus assembled by way of Boolean connectives. Please observe that while in principle the strategy could base its final answer on the whole history of the interaction, that actually depends only on certain parts of it, namely on the value of C and of D. Moreover, please notice that this strategy is indeed polytime computable, since all the replies by the player can be computed in polynomial time based on the history. Let us now switch to the second part of our talk, in which we put our computational model at work. Suppose we have a strategy for the second-order game you see on the slide. Our claim is that this cannot be pseudorandom, namely undistinguishable from any random object, in any possible sense. This is indeed intuitive, since f can query its argument function only at polynomially many coordinates, while a genuinely random function would query it in every possible coordinate. Trying to formalize this argument is, however, non-trivial, given the dependence on the key and the fact that accesses to the argument function can be done adaptively. The way out consists in showing that an adversary interacting with f can itself determine the coordinates which influence the output of f. This is done by querying f itself on carefully chosen block functions, and is guaranteed to work due to some well-known results on influential variables in decision trees by O'Donnell et al. We have already mentioned them in the introduction to this talk. We can thus state our negative result formally. It says that there is an adversary, actually a strategy, which is able, given any second-order strategy f of the kind we are interested at, to determine two inputs for such a function which form a collision and which are far away from each other and from those functions on which the adversary queried f. The strategy we have just described is efficient, and its behavior does not depend on the whole history of the interaction. In particular, the strategy called delta ignores the coordinates on which f queries its argument function, and is thus purely functional in nature. An interesting corollary is that we cannot build message authentication codes for functions the same way we do in the more traditional case of strings. The task of securely authenticating functions, if feasible at all, must thus be carried out differently, at least if one is interested in authenticating functions whose input is linearly bounded on the security parameter. It is now time to move to our positive result. Before stating it, let us see how second-order pseudo-randomness could look like. First of all, the type of a second-order candidate pseudo-random function could be the one we have already considered. The type of an adversary for it is, in turn, the one of a third-order randomized distinguisher interacting with a random or pseudo-random function and returning a Boolean. Pseudo-randomness can thus be defined following the classic recipe, namely by prescribing that the adversary's probability of success in distinguishing f from a genuinely random function is negligible. Take a look at the definition. It is structurally identical to the classic one, and it follows precisely the template we have encountered at the beginning of this talk. This being said, the definition only makes sense when p is exponentially smaller than q. Otherwise, even building a genuinely random function would not be possible. Consider the game SOF we have encountered in the previous slide, and take q to be logarithmically bounded in the security parameter instead of linearly bounded in the security parameter. The functional argument to a strategy for such a game, if deterministic, can be seen, as a consequence, as a string of linear length. It is, however, accessed interactively, bit by bit, instead of being passed as a whole to the strategy. The access pattern, by the way, is in principle visible along the interaction and can thus be accessed by the adversary. When building a strategy for such a game, trying to make it pseudo-random, one needs to be sure that not only the result, but also the way the function accesses its argument are indistinguishable from random ones. But this is possible if one assumes the existence of a first-order pseudo-random function, which helps both in introducing confusion in the access pattern and in computing the actual result. In other words, standard cryptographic assumptions imply the existence of second-order pseudo-random functions of the aforementioned type, because a first-order pseudo-random function can be built from a one-way function by way of standard cryptographic constructions. As a consequence, secure message authentication codes working on functions rather than on strings can indeed be built, although there is a price to pay. The authenticated function takes very short strings in input rather than inputs of linear length. To sum up, the main contribution of this work consists in having showed how game semantics and cryptography can be fruitful to each other. The first one offering a rigorous and simple computational model, the second one suggesting intriguing problems. We are pretty aware that the results we proved are just the very first steps towards understanding higher-order cryptography. In a sense, the surface has just been scratched. Among the topics we would like to pursue in future work, we first of all mention the study of higher-order encryption, which we have not considered so far, but which looks as interesting and as desirable as authentication. What could be even more interesting, from our point of view, is the use of our game semantics framework in the proof of correctness of cryptographic reductions, given that those can naturally be seen as higher-order transformations. Think about a cryptographic reduction which builds an adversary A out of an adversary B, both of them being second-order adversaries. Well, this transformation can be seen as a third-order program, although it has not been considered as such in the cryptographic literature. We thank you very much for your attention, and we would be very glad to answer your question during the QA session. See you there!